Okay, so let's review that example that we did last time. So we were looking at, Jack was claiming that he could hit his tee shot 275 yards on the average. So he hit 25 drives and got this sample mean, and then assuming a population standard deviation of 20 yards. And so we want to conduct a hypothesis test to see if check this claim that he can hit a tee shot 275 yards. And so this was our hypothesis. Remember, we have the null hypothesis. And so what would the null hypothesis be in this case? Yeah, so the null hypothesis is that he indeed hits the drives 275 yards on the average. Okay, that's his claim, that's the null hypothesis. And so our alternative hypothesis was he's just not that good, right? He's just not that good. So it's, yeah. So normally, so this was a left or a right-tailed test. We call that a left or right-tailed. Left, right? Because we're going to reject the null for low values, right? So for low values, and normally there would be more indication of that. This is kind of a little vague that this is a left-tailed test. I told you it was. Okay. So normally in the problems it'll be very clear that you're doing a left-tailed or a right-tailed test, and if there's no indication of left or right-tailed, then it's just two-tailed. Okay. So this is a little vague, and I kind of said that was the implication here. That we're really checking to see if he's at 275 or something less. Okay, and then the significance level that we picked for this example is 0.05, which means a 5% chance of a type 1 error. And what was a type 1 error again?
Rejecting the null hypothesis when we should not have.
Right, so a type 1 error is, he does, in this case, he does hit it 275 yards on the average, okay? But because of the sample, we took the sample as the evidence, the sample led us to believe that he doesn't, and we rejected the null, when this was just a really unlikely sample, right? So the information that we had didn't result in us making the right conclusion that he does indeed drive it, or all right. So remember that we either reject the null hypothesis or we do not reject it. Okay, so if we reject it, we're saying that he doesn't hit it this far, and we're 95% sure of that, or there's a 5% chance that we rejected incorrectly, right? We rejected incorrectly. Okay. So we did that. So and this is the process that we went through. So we just stated the null and alternate hypothesis. We discussed the logic. So obtain a precise criterion for deciding whether to reject the null hypothesis in favor of the alternate hypothesis. Okay, so that's based on the z-score of 0.05. No, sorry, the significance level of 0.05. We came up with a breaking point. Our criteria was a z-score based on a significance level of 0.05, where it was kind of the dividing line of rejecting or not rejecting, and we came up with
-1.645.
So if this mean of 264.4 yards ends up with a z-score more negative, lower, further to the left of negative 1.645, we're going to reject. So let's see the picture for that. So we got that z-score was negative 1. So that's the z-score for a confidence level of 5%. And that means there's an area to the left of 0.5%, and that's the place where we're rejecting the null. That's where we're going to reject the null hypothesis. Because why? Because the sample average was too low at a 5% significance level for us to say that he might be able to drive at 275. Okay, so at a significance level of 0.05, we're asking where does the sample lie? Where does his sample mean of 264.4 lie? If it's to the left, then that's just too low of a sample average for us to say that he might be able to drive at 275 yards. But if that sample average gives us a z-score greater than negative 1.645, then what's our conclusion? We do not reject, and we say maybe. Yeah, so it's very well may be that he can drive at 275 yards on the average. Okay, so what was the z-score that we got for the sample mean? So remember we took 264.4. We've done this before. Yeah, this is how we get a z-score for a given, and divided by 20 over, right? That's old hat, we know that. And we got the negative 2.6 something.
Negative 2.65.
So for that sample mean of 264.4, and what is that number? What is that? 2.65 what? Standard deviations, right? Z-scores are measuring how many standard deviations. What was our critical value? How many standard deviations was our cutoff for reject or non-reject? Negative 1.645. So conclusion? What do we decide? So we look at that and we say his sample mean gives us a z-score less than negative 1.645, or to the left of negative 1.645. So according to the sample that we got and the significance level that we used, do we reject or not reject? Reject. And the conclusion is? He's lying. He actually can't hit it 275 yards. But this is at the 5% significance level. What does that mean?
5% chance we could be.
5% chance that
He might be able to do
that. Right. So there's a 5% chance that the sample we got was he just happened to hit those 25 drives really low for him. And we got this sample that just happened to be like an outlying sample. It's not an indicative sample of what he can do. There's a 5% chance of that. But if we're willing to live with that 5% chance, then for sure we could say he doesn't drive at 275 yards. Okay? That we reject it at the 5% significance level. So it's not black and white, right? It's not this black and white thing. We don't know absolutely for sure that he can't do that. But we're 95% sure he can. There's a 5% chance that this sample led us to wrongly reject, right? Incorrectly reject the null. Okay, but notice also, is this negative 2.65, is it kind of is it close to negative 1.645, just a little bit to the left? Yeah, how many standard? It's a whole nother standard deviation over. So this is, compared to the negative 1.645, this is significantly further over. So there's something else we can consider here. If we think about the z-score that we got, so say here's the curve. Again. Okay. So if we got negative 2.65 standard deviations to the left, doesn't it make sense to look at this significance level? Because yes, we crossed over into the rejection region, but we crossed so far over that let's find that value right there. So what is alpha for z of negative 2.65? Can you find that? So we should all know how to do that using our z table. Okay, 0.004. So what percent is that? 0.4%. So about a half of percent, right? Less than 1%, about a half a percent. So by getting this z value of negative 2.65, yes, we reject at the 5% significance level, but then we can also say something a lot stronger than that, right? So what can we say now? The fact that we got this very low z-score, or big negative, right? That means our confidence that he can't hit at 275 just went up from the 5% significance level. So what significance level does negative 2.65 indicate? A 0.4% significance level, meaning what is really the chance that we're making a type 1 error for this z-score? It's not 5%. Do you see? Like half a percent. Do you see? So yes, 5%, the 1.645 for the 5% was the cutoff, but really our z-score indicates that because it's so far down, and it really indicates that the probability we're making a type 1 error is like less than half a percent. So our by getting that z-score negative 2.65, we're a lot more confident that we correctly rejected the null than 5% significance. So this is like the true percent chance that we made a type 1 error. Okay, this is called the p-value. So the p-value is the significance levels associated with the actual z-score that you get from the sample. So by getting that z-score that was much, much more negative than negative 1.645, we're much, much more confident than just 5% significance. We're confident to less than half a percent now that we made the right decision by rejecting. Does it make sense? Blank stares. Why not? Good there. Okay. All right, anybody have a question on this example? Right, so this is a really great real world thing, right? this guy says, I can hit it 275 yards, and then you're just like, prove it. Okay, so he hits the ball, he hits it 25 times. We get the data, and then we find out. Now, from the data, there's less than a 1% chance that he was right. There's less than 1% chance that he actually can't hit it 275 yards based on the sample that we took. Questions before we go on? Last chance. No? Okay. What's that? No, of course not. It can be about all kinds of things. I was just reviewing that example from last time we did it fast. Okay, so this is just a visual of two-tailed versus left-tailed and right-tailed and what the rejection region would be. So we just saw the left-tailed test, comparing the mean being a certain value to, no, it's not that big, right? It's less, the mean is less than that. Right tail is, the alternative hypothesis is no, the mean is greater than our null hypothesis. And then the two-tailed is just about, the mean is different from the hypothesized mean. So that could be greater or less. So that's just a summary slide. Same thing here, and this is just showing how alpha and the z-score compare, right? So this is nothing new. Alpha is the significance level, it's the area under the curve, it's the chance of making a type 1 error. And then when you have a two-tailed test, that alpha has to be split evenly to either side, right? So at the 5% significance level, say at the 5% significance level, then the area on either side is 2.5%. So alpha over 2, so this area right here. So at alpha equals 0.05, that area is 0.25. So when you go into the z table, you're not using 0.05 for the two-tailed test. You're using 0.025. Okay, this is a summary of what we've done. It's not worth copying it all down. If you want to, just go back to the video. We should just work examples. Okay, so let's do this one. So so this is the top speed of cheetahs. Okay, so it says one common estimate of the mean top speed of cheetahs is 60 miles per hour. So like when people are in conversations, like, cheetahs can run 60 miles per hour. So is it true or not? So we've got a sample of 35 cheetahs and their top speed. And we're going to look at the 5% significance level. Do the data provide sufficient evidence to conclude the mean top speed of all cheetahs differs from 60? Assume that the population standard deviation is 3.2. Okay, so first of all, we're going to do set up our test, which is the null and the alternative hypothesis. And so first of all, is this going to be a left-tailed, two-tailed, or right-tailed test? Left-tailed, two-tailed, or right-tailed test? He wants two-tailed. Agree with that? Okay, so like I said earlier, though, it doesn't say anything about that. So whenever the driving one was kind of an exception to the rule, you had to kind of read into it that way. But the questions will be very clear as to whether it's left-tailed or right-tailed, and if it's not, then it's two-tailed. So there's nothing here about saying we want to find out if they run faster than that or if they run slower than that. It's just whether or not a good estimate for their average speed is 60. So that would indicate what? Two-tailed. All right, so we're going to say that the null is that the mean speed of cheetahs is 60 miles per hour, and the alternate is what?
It's not 60.
Not 60. And that's our two-tailed test. Okay, so what would what are we at? So what question are we asking here with this test? What are our two potential outcomes and what do they mean? What are the two potential outcomes of this test and what do they mean? Okay, Heather.
One of them is that the average is greater than 50 miles per hour, and so that means cheetahs are faster than on that on average. And one of them is that it turns out to be less than 60 miles per hour, and that means cheetahs run slower than that.
Okay, but those aren't the two possible conclusions from the test. That's true, but there's two possible conclusions we're going to get from the test. So,
that we accept the value that is 60 miles per hour,
okay.
or that it's less than or greater than 60 miles.
Okay, so is the test the possibilities from the test that we accept the null hypothesis or reject the null hypothesis? Are those the possibilities? No, that's not correct. So what are so the two possibilities are there's two possibilities from a hypothesis test. One of them is reject the null hypothesis. Reject the null. And what would it mean to reject the null? What would we be saying? What would we be saying in this case, in this context, if we rejected the null? Naomi, do you know? What would we say if we're rejecting the null?
That the speed of the cheetah is not equal to 60.
That's right. Speed of the cheetah is not 60 miles per hour. That's what it would mean to reject the null hypothesis. To some degree of certainty. To some degree of certainty, that's our significance level, that cheetahs do not run 60 miles per hour. What's the other possibility? Yeah, Randy.
You do not reject.
Do not reject. This is not the same as accepting the null. Okay, so this is important. We do not reject the null. And what does that mean in this context? What does not rejecting the null? And how is it different than accepting the null? Randy, yeah.
So I think this is right. You would say by not rejecting it that it very well could be 60 miles per hour and that you don't have enough proof to say that it's not.
Right. So we don't have enough evidence to say that it's not 60 miles per hour, which is different than saying it is 60 miles per hour. Do you see that? So that's how these hypotheses tests work. Accepting the null is never a conclusion of the test. It's always that we don't reject the null, which says it could be, it might be 60 miles per hour. There's not enough evidence to say otherwise. That's what not rejecting the null is. Okay, so let's do it. So let's just highlight that. Not enough evidence to conclude cheetahs don't have an average of 60 miles per hour. Average top speed. That's what not rejecting means. There's not enough evidence to conclude that cheetahs don't have a 60 miles per hour average top speed. They very well could have an average top speed of 60 miles per hour according to the evidence. Okay, so this is for your notes. Let's see how you do. Okay, so at 5% significance level, what's going to be the area on each side? 0.025 area either side, and that's how you're going to get the critical value for what you're testing against for z. That's going to give you z alpha, right? Or in this, so z alpha over 2. It's going to be based on 0.025. And then you're going to find the actual, what's called the test statistic. The test, so this is called the critical value. This is called the critical value. The test statistic is the z value from the sample. And this one is called the critical value. Critical value is the breaking point between rejecting and not rejecting. So you're going to do both. You're going to find the critical value, and you're going to find the test statistic, make a diagram, and make your conclusion. Okay? This is for your notes. This is for your notes. Work together. So if you get less than 10 out of 20, it's because you missed a day of class.
Same thing.
Safely.
Okay, two-tail. Because we don't, they want to know, so we do two-tail. So, we do that.
I don't know how you got it that way.
Jason.
Well, I went over here to the Z, and I looked up the 0.25.
So you looked for that.
Yeah.
Oh, so you did it backwards.
Okay. And then here it's supposed to be plus 196.
Okay.
Okay.
I had no idea.
Okay. So we got that. Now the next step is to value from the sample. So I have. We're using this formula, and this is what
I didn't know which one to use. So I did not.
I did it if I'm in parentheses. So what I did was I put in parentheses 59, 26 minus 60. We divide that by 3.2
It's a really little number.
minus 0.8. 876. Okay. Keep it in threes.
Sounds good.
So that would be the z value for the sample. So
Do we have to do anything with the table with that?
now this is higher than that. we would accept the null. Because there's a good chance, there's a good possibility that they do run 60 miles an hour.
Well, I guess to figure out like the marks.
Yeah.
To know the line. Okay.
Here, do not reject H. So it's two tails, so we would not reject that. So continue to agree not to reject it. Oh, that's it, yeah.
What is our Z for this?
We got that one is 1.96. Yeah. Negative 1.96. Thanks.
So what'd you get for that? Test statistic? Negative 0.87.
to the mean.
Is that?
So you're like once you know the sample.
And then if R is
Sample standard deviation is almost one standard deviation closer to the mean.
Yeah, it's not even it's not even close to the breakpoint, right?
So wouldn't your conclusion be do not reject?
Absolutely. Okay, so you should have gotten the critical value of 1.96 or plus or minus 1.96. Did you get that? That's our breakpoint for our non-reject region. It's here in the middle. So this is from here to here, from negative 1.96 standard deviations to positive 1.96 standard deviations. Do not reject, right? But then if we get too far away, right? If our sample indicates a standard deviation at less than negative 1.96 or greater than 1.96, well then that sample is saying it's too far away from 60, and we have to reject, right? So the rejection region would be out here and out here. Would be our rejection region. So how about getting the critical value, which we're comparing against? The critical value sets up our rejection and non-rejection region. Any questions about that? Okay, and then there's the test statistic, which is the z-score according to this sample. The z-score according to that sample measured against the hypothesized mean of 60, right? So we took the mean of the sample, subtract the hypothesized mean, and then divide by the standard deviation of the sampling distribution, right? So it's 3.2 divided by square root of 35. And so you should have gotten a test statistics of negative 0.876. Questions on that? Is that what you guys got? And so then, is that in the non-rejection region or the rejection region? That test statistic. Do not reject, right? Do not reject. Why? It's close enough. So as a mean of 59.526 miles per hour with this size of a sample is close enough to 60 that we would conclude what? It's close enough to 60 that we would say, what's our conclusion?
Do not reject the null hypothesis.
Okay, so we do not reject, which means what? So we're going to say do not reject. Which means what? What does it mean in this context to not reject the null hypothesis? Paul?
That there's a possibility that cheetahs run a mean of 60 miles per hour.
Yeah. Not enough evidence for us to say otherwise. So it's very possible that cheetahs have a mean of 60 miles per hour, and there's not enough evidence to say that they don't. There's not enough evidence to say they don't run 60 miles per hour on the average. Are we concluding that the mean speed of cheetahs is 60? We're not doing that. We can't do that. All we can say is maybe. Maybe it's not enough evidence to rule it out. Not enough evidence to rule it out. It's possible that they run 60 miles per hour. That's why it's called do not reject instead of accept. So not enough evidence. To say cheetahs don't run 60 miles per hour on average. Questions on this example?
Only need to know that to figure out what those boundaries are.
Yeah, so that's called the That's the critical value. The critical value sets up what the non-rejection and the rejection region is. And so then we get the test statistic and we figure out which region it falls in, which came from the z-scores, which we call the critical values. Yes, sir?
So finding the area under the normal standard curve for like the z-score that we got, negative 0.876, we only find that if we reject it? Like how we did on the last one, we found that it was 0.4.
Oh, the p-value?
Yeah, the p-value, yeah.
Yeah, so no, we could find the p-value here. And yeah, so let's do that. So what's the p-value for this one?
We got like 0.1894.
Okay, so p-value, the p-value. So that means there's, for this z, for negative 0.876, you got this area to the left of, so when the z-score is negative 0.876, what'd you get for that? 18.94%. So is that the p-value? Not subtract. So it actually, what would we do? Remember, alpha is all the area of the non-reject region. So what would you do? What's that area then?
Area to the right of.
It's also 18.9. This is a two-tailed test. So this is half of the percent because it's a two-tailed test. So therefore the p-value is 37.8 or something, 88. So based on a z-score of negative 0.876, that gives you an area to the left from your table of 8 to 18.94%. Because it's a two-tailed test, you also have the area to the right of positive 0.876. And all of that area is the significance level.
Why would you go positive?
Well, what do we do? For 5% significance level, what do we do?
Two-tailed.
Two-tailed. So we did half of that on one side and half on the other. So when you took negative 8.76 and got an area, the chart gives you just the area to the left. So that's like, this is alpha over 2 for a two-tailed test. So then the rest is, there's also the right tail, right? There's also the right side, which is the same amount. That's alpha over 2. So then the p-value is the alpha. It's the significance level.
And we only need to find that if we reject the null.
No, you can find it in any case. But yeah, it makes more sense when you're rejecting. So this is good practice to find it, but in terms of making sense of it, it doesn't really apply when you don't reject. So it's when you reject that it kind of makes sense, like in our last example. Makes sense to talk about it, okay? But good practice to find it. Other questions? Okay, so now you guys, your turn for the sheet. You got 2 to do. Okay, so just 10 minutes on these. 10 minutes to do these. Work efficiently. Oh, so let me tell you what I want you to do.
So this is your sample.
Okay, so for both of them, I want you to do these 4 things. Create the test, which consists of stating the null and alternative hypotheses. You're going to execute the test, make the conclusion, and interpret it with a sentence, and then find the p-value. So all 4 things for both. If you're stuck, get help. We can help and come around. What's that? What'd you say?
She owes a lot of people coffee.
Oh, you owe people coffee.
We're helping you all the time. This is a
Okay, so I know it's not optimal and it's not satisfying, but if you're halfway through the second problem, don't keep working on it because we need to do one more thing for Fridays for the homework for Monday. Okay, like I said, as long as you have some work, you're fine on number 2, and we'll just look at number 1 more closely. Okay. All right. So remember we said it's kind of unrealistic to just take a sample, but yet know the population standard deviation, sigma. Remember that? We did that with confidence intervals. What's more realistic is you just have the information from the sample. You don't have this population standard deviation. And so we're going to do the hypothesis test for when you don't know the sigma, the population standard deviation. Okay? So don't write all this down. But it's the same thing, except now we're using the sample standard deviation, which kind of makes more sense. You take a sample from the population, and you would just be using the information from the sample, which would be the sample mean and now the sample standard deviation. But then that's no longer a Z chart score, and that takes us to the T, using the T score, okay, or the T chart, because it's a different distribution when you're using the sample standard deviation. So we do everything else the same, except now we're using the T chart to get the critical value. So let's do an example. Let's do TV viewing. Okay? So it says we're going to do this for your notes. This is not for the sheet. So we'll do this for the notes together. Okay? So it says a random sample of 20 people. So our N is 20. Okay, the following number of hours television watched per day. So for the sample of 20, we had a mean of 4.76 hours of TV watched per day. Scary, right? It's a lot of TV a day. And then the sample standard deviation of 2.297, right? A more realistic situation. It's not really, how would you know the population standard deviation? You know, more realistic is you just get the standard deviation, you have the standard deviation from the sample, S, okay? All right, and so back in 2005, the average was 4.55. So our null hypothesis is that that average is still 4.55 hours per day. The alternative hypothesis is, does the data provide sufficient evidence to conclude the amount of television watched per day differed from 2005? Left, right, or two-tailed test? Two-tailed. Sorry, this is not right. The null hypothesis is that the mean equals, right? The notation is important. The alternative hypothesis is that the population mean does not equal 4.55. All right, and we want the 10% significance level. So let's draw the picture. A two-tailed test for the 10% significance level means what for each side? It's the 10% significance level. That means 0.05 there, and 0.5% on either side. So now to get the critical value, we're not going to use the Z table because we're using the sample standard deviation, not the population standard deviation. So we want to use the T, and that means we need degrees of freedom. Remember that? So the T value with how many degrees of freedom? 1 less than the sample size, so our degrees of freedom is 19. So when the degrees of freedom is 19, you want 5% of the area to the right. I think that table shows area to the right. Is that right?
Yeah.
And we want 5% to the right in order to have a 10% significance level on a two-tailed test. She got 1.729. Second that. Awesome. And so then, because it's a two-tailed test, we're also going to need this one, which is negative. That's easy. Should be, anyway. So 19 degrees of freedom, and a two-tailed test with 10% significance means 5% on either side. You're going to look in the table where this is 5%, right? That's what you're going to go in the table with 19 degrees of freedom. You should have got a T of 1.729. So that's what's called the critical value Where's our rejection region? So where's our rejection region? The middle or the outsides? Outsides. We're different. We're saying we're going to reject the fact that the mean is 4.55 because it's something different. It's too far away from 4.55 outside of this range here. So this is our do not reject region here. Do not reject is there. So now we need the test statistic. And the test statistic is our sample mean, which is 4.76 minus our hypothesized mean over the adjusted standard deviation. Divided by what? Here is our test statistic. Crank it out as soon as you get it. Tell me what it is.
Why is it not over the square root of 19?
Because it's always the square root of n. The degrees of freedom is just for using for the table. It's always over the square root of n. As soon as you get that value, shout it out.
0.410.
Say it again.
0.410.
0.410. So the mean of 4.76 gives us a t value of 0.410. And where does that land? Rejection or non-rejection region? Well inside the non-reject, right? So we would have to have had exceeded 1.729, but we're here at 0.410, which is relatively close to the hypothesized mean. So this sample of 4.76 is sufficiently close to 4.55 that we would not reject the null hypothesis. And by not rejecting the null hypothesis, what is our interpretation of that? Do not reject the null. Means what in this case? Go ahead, Daniel.
That the average hours spent watching TV has not differed since 2005.
Not quite. We can't make that conclusion.
Oh,
Remember what?
there's not enough evidence to reject.
And rejecting means what? So there's not enough evidence to say that.
The viewing hours have changed.
Right. There's not enough evidence to say that the viewing hours per day has changed. There's not enough evidence to say that this is an increase in viewing hours, or a change from 4.5 hours per day. So I'm actually glad you said that because it doesn't say that. We're not concluding that the average hours per day has not changed. We're saying there's not enough evidence to say that. Not enough evidence to say that the average hours per day has changed. Make sure your name and date is on the page.